So, good evening and welcome to the week 8 live class session on the course Experimental Biochemistry, which is being taken by Professor Shomode and Professor Shagota Dasgupta of IIT Kharagpur. I am Srijan Sen from IIT Kharagpur, and today we'll be taking your week 8 live session. So, first we will be discussing the week lectures in brief, and then we will be solving a few question and answers. Okay, if that's good, I'm sharing my slides with you all, and hope you can enjoy the class. Yeah, so I guess my slides, my screen is visible to you all. Okay, so fine then. Okay. So in today's class, we would be mostly discussing about enzyme kinetics. So we have talked about proteins, we have talked about so many things. So we will be talking about another type of a protein, which is an enzyme. We call it as the biocatalyst. So we know about enzymes. So basically, enzymes are proteins that increase the rate of the reaction by lowering the energy of activation. They catalyze nearly all the chemical reactions taking place in the cells of the body, and the beauty about enzymes are that they are not altered or consumed during the reaction, so you can reuse them if that's possible. So in this way, enzymes are very beneficial. So when we compare enzymes with chemical catalysts, so there are a few differences which we will know about them. Rather, there are so many things we call that enzymes are biocatalysts. So they do a similar kind of a reaction as that of chemical catalysts. So what are the common properties that are shared by the chemical catalysts when we compare them with enzymes, is that enzymes are neither consumed nor produced during the course of a reaction, so does the chemical catalyst. And enzymes do not cause reactions to take place, but they greatly enhance the rate of the reactions that would proceed much slower in their absence. So the similar kinds of a tendency does the chemical catalysts have. So they alter the rate but not the equilibrium constants of reactions that they ultimately catalyze. Okay. However, enzymes are also very different from the chemical catalyst, because we know that enzymes are biocatalysts. So biocatalysts, in the mean, we can call them as proteins. They are highly specific compared to the chemical catalyst and produce only the expected products that from the given reactants or the substrate. So there are no chances of side reactions, which is definitely possible when we are treating with a chemical reagent or a chemical catalyst or something like that. Thirdly is that enzymes shows high specificity towards one substrate, and it exhibits a broad specificity using more than one substrate, so increasing its applications widely and specifically. And also that enzymes functions within a moderate pH and a temperature range, so this can be a drawback sometimes. Therefore it's actually very much feasible with the proteins or some kinds of biological molecules. But chemical catalysts might be harsh, they can be operating on a very wide range, so therefore we can tell them that they are not very specific. But definitely if you want to use chemical if you want to use catalysts over a very wide range, you can definitely use it. So what happens when we have an enzyme or we don't have an enzyme? So this is a very nice cartoon from where you can understand. So in normal reaction, what happens, that there are a few reactants present over there, and this is the product side. And this is the energy barrier that these frogs have to cross to reach to the side of the products. Now when the energy barrier is very high, which is most of the which happens in most cases for many reactions or so, the number of frogs that will be able to cross this barrier is very less. Now, so this is happening because the reaction proceeds at a slow rate due to very high activation energy, and it's difficulty for the frogs to cross the threshold. Now when you have a particular enzyme, what does it do? So the enzyme just removes a few of these rocks, thereby lowering the limit or the threshold, and the reaction proceeds at a significantly faster rate, as you see a reduced energy barrier and an activation energy. So the number of frogs being able to cross the barrier or reach to the product side is much more. So with this, we come to the concept of free energy. That's very important for describing any such thermodynamic function or so. Great. The concept of free energy comes with, you see that here we have a girl who is sliding so it's playing on a slide. So we have more free energy, which indicates that less stable, greater work capacity. So free energy decreases, direction of the spontaneous change occurs. So when delta G is less than 0, it means that the reaction is feasible or it moves in the forward direction. So it can be so the change in the direction of equilibriums can be the change can be harnessed to perform work. So here we are relating free energy with work. So more free energy means less stable, greater work capacity, and less free energy means more stable, less work capacity. Okay. So when the free energy of the reactant is greater than the product, the free energy changes for the reaction is negative, and it happens spontaneously. So delta G equals to delta of the products minus the reactants. If it's negative, it moves very quickly to the forward reaction. Whereas for the reverse case, where delta G is greater than 0, then it's in a positive value, so the reaction does not proceed spontaneously, and the reverse reaction, so it follows a backward reaction. So every equation, when we write or whenever we are writing about a reaction where there is an involvement of an enzyme, or there is we are not very sure about it, how is it going to proceed, we should be writing it in a reversible manner, where there should be two arrows given in manner such that the two reactions occurring are in equilibrium, such that we know that there is a chance of both the reactions to happen together. Now, we should be knowing about the components of enzymes. So what does an enzyme comprise of? We know that it's a protein, it's composed of amino acids and so, but there are different parts that form the enzyme or form an enzyme. So we have the apoenzyme, that is the protein portion or the inactive portion, that is the major part of enzyme, but that is inactive. So what's the activator? So the activator can be a cofactor, that's a non-protein portion that comes and binds with this apoenzyme to form the holoenzyme, that's the whole enzyme or the active enzyme. So we have the apoenzyme plus the activator, or a cofactor can be some ions, or can be there are different kinds of prosthetic groups or so. So then you have a substrate that can go and bind with it and carry out a reaction. That's fine. So what are these activators? So these activators are basically your cofactors, which can be your coenzymes or some kinds of essential ions, like um, you have different kinds of metal ions or metallozymes that tightly bind, or even small metal ions that loosely bind to it. Or you have the coenzymes that have the co-substrates and the prosthetic groups depending on its binding ability. So these are the different kinds of activators that basically make your apoenzyme a whole holoenzyme, and at the same time it activates your enzyme to carry out the to reduce the activation energy and carry out a faster reaction. So what's an active site of an enzyme? So the area of the enzyme where the substrate or the substrates attached to it is called the active site. So the binding site is called the active site, where it goes and attaches. So it's very important to know that the binding site holds the substrate in place, but you can have a very different active site or a catalytic site. So catalytic site is the place where your reaction is occurring, and the binding site is the portion where it holds the substrate in a particular position. So if you see over here, the substrate enters the active site of an enzyme, it goes and binds over there. You get the enzyme substrate complex, and then so this is the substrate, it carries out the reaction in the presence of this enzyme, and you get a different kind of a product. So after the enzyme is done with its work, you get the enzyme product complex, and the products leave the active site of the enzyme. The enzyme is maintained in its own form, and you get from the substrate you get the two products. Okay, but when we talk about enzyme kinetics or whatsoever is happening over here or in any place, it's based on a particular theory. So these things works very well. Okay, so the different theories of enzyme kinetics, the first one being the lock and key model. From the name, if you can understand that, so there is a lock, there has to be a lock, or there has to be a one portion of the thing has to be a key. Okay, so for this, there are a few barriers as well as a few advantages. You can look into it. So, what is the theory of lock and key model? So, it's based on the active site has a rigid shape. So, only those substrates that fits into that active site can be able to carry out the reaction faster. Otherwise, it's very difficult. At the same time, the advantage of this particular model is that it's very specific. Like if you have an enzyme that is designed for a specific substrate, it is much more better, because then it won't be binding to some random substrates and carrying out random reactions. Might get some undesired products, which is not at all important for you. But this rigid shape also restricts the number of substrates to be able to form the products, because the enzyme is not able to bind to the substrate and carry out the reaction. So these are the few advantages and the disadvantages. And also this is a very older model, so it does not work for all the enzymes. Like I was telling, it does have a few disadvantages. So based on the disadvantages what we had there, a different theory was built up, that is the induced fit model, where the shape of the active site is very much flexible, so it's not that rigid. So the enzyme, the active site and the substrate adjusts to the maximize the fit, and it improves the catalysis. So you have an active site like this, but your substrate is somewhat diamond shaped, so it cannot go and bind over here. For this, the active site should be flexible enough to change its shape to a desired substrate, and then it carries out the reaction. So therefore it has a greater range of substrate specificity. That is also true, and this model works very well with a wider range of enzymes. So we have two theories, the lock and key model and the induced fit model. Now, so based on all of these theories, or considering all of that, the IUMB system classified the enzymes into 7 types, where we have the oxidoreductases, we have the transferases, hydrolases, lysases, then isomerases, ligases, and the translocases. So there are different types of enzymes, each having different activities. Some can be used for ligation, others are used for different for formation of the isomeric products and all. Then redox reactions, transfer the ability of the mobilities, then adding water or dehydration reactions, and so on. Okay. Now, a very important term that we need to keep in mind is the turnover number. So, what is that? So, most enzymes catalyzed reactions are highly efficient. Now, they proceed from 10 to the power 3 to 8, 10 to the power 8 times faster than the uncatalyzed reaction. So, typically, each of the enzyme molecule is capable of transforming 100 to 1000 substrate molecules into product each second. So turnover number is basically the number of molecules of substrate converted to product per enzyme molecule per second is called the turnover number. So what is that? So you have a few molecules of substrate. So if there are 2 molecules of your substrate that is converted to a product, okay, so one enzyme in 1 second is able to convert two molecules of substrate to a product, we can call the turnover number of that enzyme to be 2. Now there are several environmental factors that affect the enzymatic reaction. One of them is the temperature. So the temperature is very vital because the human body temperature is 37 degrees. So we need an optimum temperature for a reaction to occur inside the body, and enzymes are very well functional at 37 degrees. So therefore an optimum temperature is required for the function of the enzyme. Also another factor is pH. That is also very important because it affects the rate of the enzyme substrate complexes. So most enzymes have an optimum pH of 7. However, some like to work at alkaline pH, like you have the trypsin, or even at acidic pH where you have the pepsin. Okay, so it's all based on the turnover numbers. So we need higher turnover numbers for enzymes because we need the optimum activity of the enzyme. Okay, so we need a system or a condition where the enzyme works fantastically, maybe at a particular temperature and at a particular pH. Now the rate of the reaction basically increases as we increase the substrate concentration, at considering that the enzyme is same over here. So you see the concentration of the substrate is increasing, and at one point it gets saturated. Now maximum activity occurs when the enzyme is saturated, when all the enzymes are binding the substrate. So that's the point when you get the maximum activity, and the point at which the enzymes are saturated such that it cannot bind any more substrate, we call it as the maximum velocity, or the VM. Okay, so here you see the enzyme activity increases and all the enzymes are combined with the substrate, so this is maximum activity at VM. Now the kinetics of enzymes is that it follows zero order kinetics when the substrate concentrations are high. So what does zero order mean? So zero order means that there is no increase in the rate of a reaction when more substrate is added. Okay, so one example is given over here. Now we will be focusing on a few the important equations over there. So what we see over here is an enzyme that binds to a substrate, and you have a reversible reaction where you have the enzyme substrate complex giving you the enzyme plus the product, and your K1 is the rate constant for the forward reaction, and K minus 1 is the rate constant for the breakdown of the complex, the enzyme substrate complex to the substrate, and K2 is the rate constant for the formation of the products. Now if we combine all of this, we can tell that when the substrate concentration becomes large enough to force the equilibrium to completely form the enzyme substrate, the second step of the reaction becomes the rate limiting, because there is no more of the complex that can be made, and the enzyme substrate complex is at a maximum value. Now the concentration of the enzyme substrate is the difference between the rate of the formation of the complex minus the rate of its disappearance. So you see that here we want to derive an equation where you have the rate of the reaction equals to your K2 multiplied by the concentration of the substrate. Now this thing is basically your complex concentration, the rate of the complex concentration, which is equal to K1 into enzyme concentration and substrate concentration minus K minus 1 into your complex concentration minus K2 of the complex concentration. And assuming the thing to be in equilibrium, K minus 1 is very greater than K2. So the formation of the product is so much that the formation of the reverse reaction can be neglected. So we can assume that Ks equals to your K minus 1 divided by K1, where we have the concentration of the enzyme and the substrate divided by the complex concentration. So Ks is the dissociation constant for the enzyme substrate complex. Now, according to the steady state approximation, what does it say? That the transient phase, where in the course of the reaction the concentration of the ES does not change. So you see the substrate concentration decreases, the product concentration increases, but with time the concentration of the complex does not change. So we can consider that the rate of this change in the complex concentration is zero because it's not changing. So the total enzyme concentration is equal to your enzyme concentration in your initial steps plus in your complex. So when you combine the equations that I showed previously as well as this, you get something big equation like this, where you arrange it and you get the final equation to be your enzyme complex concentration equals to your total enzyme concentration multiplied by the substrate concentration divided by Km plus S, substrate concentration, where your Km equals to K minus 1, that is for the backward reaction, plus K2, that is for the product formation, the rate constant, and divided by K1, that's for the forward reaction to the formation of the complex. Now, whatever steady state approximation you consider and you do it, you get a Michaelis-Menten equation where V naught equals to your Vmax. So you see over here, you see a very similar kind of an equation where your Vmax equals to your K2 into the enzyme total enzyme concentration. So that's Vmax. So you need to remember the Michaelis-Menten equation, because from here there will be multiple questions. And you see Vmax, so V naught equals to Vmax by 2 at half concentration. So when the V naught equals to Vmax by 2, that is at the maximum velocity, or when Vmax or when V naught equals to Vmax, at that point your when V naught is Vmax by 2, that is the point when Km equals to your substrate concentration. So these are the few things that you definitely need to keep in mind, because there will be multiple questions associated with it. And then you can plot a graph based on this Michaelis-Menten theorem, where you have the Km, then 2Km. It's reaching a constant value. So at Vmax, so this is your Vmax. So when Vmax is half, or when V naught is Vmax by 2, that is the point when your substrate concentration equals to your Km value. and this Km value widely varies among different enzymes. So Km can be expressed as this, so you need not remember these equations, sorry, but you need just for your information. So as Ks decreases, the affinity for the substrate increases. The Km can be a measure for substrate affinity if K2 is less than K minus 1. So here we have the double reciprocal plot where the same equation is, so we take the inverse of that 1 by V naught equals to Km by V max 1 by S plus 1 by V max. So your 1 by V max is the point over here, and this is minus 1 by Km, and your slope is basically Km by V max when you are plotting 1 by V naught versus 1 by S. Okay. So from here you can calculate the slope. So if you know one of the value, maybe the slope, or definitely you can get the slope. So if you know Vmax, you can get the Km, or if you know Km, you can get the Vmax. Also from here you can get Vmax, as well as you elongate this curve to the negative side, then you get 1 minus 1 by Km. So that's the double reciprocal plot. Then you have so many other plots, like the Lineweaver-Burke plot, where you have slope equals to Km by Vmax, 1 by V naught, intercept is equal to 1 by Vmax, and when it's extrapolated, x-intercept is equal to minus 1 by Km. So turnover number, I just spoke about the turnover number. So Kcat is how many reactions an enzyme can catalyze per second. So Kcat equals to Vmax by the total enzyme concentration. So there are different assumptions that are taken. So for Michaelis-Menten kinetics, you have K2 equals to Kcat. So when substrate concentration is very less than Km, very little complex is formed, and enzyme concentration equals to total enzyme concentration, and V naught is equal to K2 by Km of the total enzyme concentration multiplied by the substrate concentration, and Kcat by Km is a measure of the catalytic efficiency. Now here we were speaking about the catalysis reaction, but these enzymes also, we need to understand the inhibition kinetics. That's very important, because we need to inhibit the reaction, because an enzyme cannot continuously go and carry out a reaction forever, so we need inhibitors. So inhibition kinetic, we need to understand the inhibition kinetics as well. So there are three types of inhibition kinetics: competitive, mixed, and uncompetitive. So competitive, where the inhibitor competes with the substrate in binding to the enzyme. So you have the enzyme and the substrate over here. So this is the normal equation, but in the presence of an inhibitor, the enzyme binds with the inhibitor and the substrate does not have a place to bind, so there is no reaction. And then the equation somewhat changes to like this, where you have V naught equals to Vmax into substrate concentration divided by alpha Km plus substrate concentration. So alpha is 1 plus inhibitor concentration divided by Ki. So the value increases to a bit, and ultimately V naught decreases. Okay, so more the value of alpha, so as the value of alpha increases, you can see that the Km value is, the Km value is the substrate concentration is increasing, so with the increasing inhibitor concentration. Okay, so with an increasing inhibitor concentration, you see what you see over here, you see the Km value is also increasing, and so the values changes, right? And when you do the same thing in a Lineweaver-Burke plot, then you see the double reciprocal plot, 1 by Vmax remains the same, but your x-intercept, that is minus 1 by Km, shifts. So it moves towards a more positive value over here. So 1 minus alpha km, so it moves over here. So it becomes so the value becomes the value increases with the increasing inhibitor concentration. Now you have the uncompetitive inhibition, where the enzyme can have a tendency to bind to the substrate and then with the inhibitors. So in any ways there would be no reaction, but it's a very different type of an inhibition for an uncompetitive system. You see over here with an increasing inhibitor concentration, what happens over here, that the value moves towards a more negative value, because over here we had minus 1 by alpha km, but here we have minus alpha dash by km. So alpha dash is something of the same value, but you see it changes. So both the x and the y intercept over here changes. So it's alpha dash by v max and it's alpha dash by km minus. And then we have the mixed inhibition, where the inhibitors can have a tendency to either bind with the enzyme in the first place or even after the substrate concentration. So it can be a competitive as well as an uncompetitive inhibition. So what happens over here, in this place the value of the x and the y intercept also changes, and you get somewhere joining point over here. So with an increasing ion concentration, you see this value is increasing, and you see the value to be increasing over here as well. So yeah, so you see an increase. So there are different equations. If you want, you can keep these things in mind, like the alpha dash is very important, which is equals to 1 plus inhibitor concentration divided by the k I dash. So you see over here what happens to the Vmax and the Km value. This is very very important. So when there is no inhibition, Vmax remains Vmax and Km is Km. In competitive inhibition, you have Vmax remains same, whereas your Km value increases. For uncompetitive inhibition, both Vmax and Km value decreases. And for a mixed inhibition, your Vmax decreases and your Km depends on the values of alpha and alpha dash. So it may remain the same, it can vary. Okay. If alpha equals to alpha dash, then Km remains same. Okay. So this is all about the inhibition kinetics. Okay. Now we will be discussing the question and answers. Okay, so maybe a 5 minutes break and then we can discuss the question and answers. Okay, so let us check with the first question. The site where the catalytic activity of the enzyme generally takes place is known as your option B, because I have spoken about it. So where your reaction is taking place is the active site of the enzyme. Then when the velocity of the enzyme activity is plotted against substrate concentration, which of the following shape is obtained? So you have just seen it's an hyperbolic curve. Okay, the next one is given that delta G naught for the reaction is to P is negative in the direction, so which formation will happen? So you are seeing that when it's moving towards the product, delta G is negative, that means the reaction is feasible. So ideally you should get more amounts of the product, so option A is correct. Now for the reaction where you have this, the quantities can be measured experimentally. So which are the quantities that you can measure experimentally? You can measure the concentration of the substrate, you can measure the concentration of the enzyme, as well as you can measure the concentration of the product. Okay, so yes, so you can measure all the three concentrations. You cannot measure the complex concentration or the bound one, because it does not change, as well as it's very difficult to capture experimentally, and it's because of a fast reaction. Okay. Now for a given enzymatic reaction, which of the following best describes X? X is the substrate, X is the deformed substrate, X is the other form of the product, X is the enzyme itself. So you know that the enzyme is obtained in free form once the substrate is converted to the product. So you get X as the enzyme only. Now to measure enzyme kinetics, which of the following is varied? Enzyme concentration, substrate concentration, product pH. So if you see the curve, you have plotted 1 by V naught or V naught versus the substrate concentration. So varying the substrate concentration will help you to measure the enzyme kinetics. So B is the correct option. You can check back from my slides if you have any difficulty in understanding. Okay, which of the following determines substrate specificity of an enzyme? So the complementary geometry of the substrate and the enzyme, it's very important. Then you have the complementary electrostatics, that's also an important one. Okay, the next one. In Michaelis-Menten kinetics, Km is defined as, so what is Km? In Michaelis-Menten, so you have concentration of substrate required to reach maximum velocity, enzyme concentration required to reach maximum velocity, concentration of substrate required to reach half of the maximum velocity, concentration of enzyme required to reach half of the maximum velocity. So option C is correct. Yeah, absolutely, option C. Next one. The advantage of using Lineweaver-Burk plot. So why do we want to use Lineweaver-Burk plot? We had the Michaelis-Menten. It linearizes the Michaelis-Menten equation. It's easier to extrapolate a straight line. The errors in Km and Vmx are small. The important parameters can be determined from the intercepts of the two axes. Yes, so A, it linearizes. It's easier to extrapolate a straight line. Both are correct. At the same time, all the parameters can be determined from the intercepts, thereby easing the equation. Okay, so in Lineweaver-Burk's plot, the y-intercept. So what's the y-intercept? We all know it. You have just checked it. So it's, yeah, it's B, that is 1 by V max. Then for a competitive inhibition, the maximum velocity can be obtained at. So where do you obtain the maximum velocity? So at elevated substrate concentration, the inhibitor is replaced by the substrate. So you observe increased substrate concentration. Now during non-competitive or uncompetitive inhibition, the inhibitor binds to the site which is called the, what does the inhibitor bind? It binds to the allosteric site. It does not bind to the inhibition site. It binds to the allosteric site, thereby prohibiting the enzyme to carry out the catalytic reaction. Okay. Now with increase in concentration of the inhibitor, the Km value increases in case of. Okay, it's a very nice question. So you can check over here with the increase in the inhibitor, which of the concentration changes. Yes, absolutely. So competitive inhibition, that is the correct answer. Okay. Number 14. While monitoring the activity of the enzyme in UV spectrometer, which two parameters are monitored in the instrument? Absorbance versus wavelength, time versus wavelength, absorbance versus time, time versus absorbance. It's very easy. Yeah. Absorbance versus time. Okay, no, this one. So absorbance should be in y-axis and time in x-axis. And the last question, when a sliced apple is kept in open air, it becomes brownish, which is due to oxidation of phenolic compounds in apple by enzyme O diphenol oxidase, reduction in phenolic compounds, inhibition of enzyme, inhibition of phenolic compounds in enzyme by the enzyme. Yeah. So it's because of oxidation of the phenolic compounds in apple by the enzyme O orthodiphenol oxidase. Okay, so that's all from my side. If you have any questions, you can definitely mail me back. I will be happy to answer, or if you can ask me in the next class, which will be on this Friday, then that's good enough. Okay. Okay, then thank you very much. We will again meet in the next class.